Hi. Hi everyone, welcome to this keynote session. My name is Ulf Assarsson and it's my honor to be chairing this keynote by Kavita Bala. The title is Understanding Visual Appearance from Microscale to Global Scale. And thank you, Kavita, for coming here to us today. I know it's quite early in the United States right now in this moment. Before we start, I would like to say a few words about our keynote speaker. Kavita Bala is a full professor and also the chair of the Computer Science Department at Cornell University. She's a founder of GrokStyle, a visual search company that was acquired by Facebook. She specializes in computer graphics and computer vision. She performs research on recognition and visual search, material modeling and acquisition using physics and learning, and physically based scalable rendering, and also perception. Kavita Bala is an ACM fellow as of 2020. She has served as the editor-in-chief of Transactional Graphics and been associate editor of TVCG and CGF. She has served many times on the SIGGRAPH and SIGGRAPH Asia paper advisory boards. She is co-author of the book Advanced Global Illumination. She has been paper chair of SIGGRAPH Asia, Pacific Graphics, and Eurographics Symposium on Rendering. She has received the NSF Career Award and multiple teaching awards, 2006, 2009, and 2015. I'm very glad that you can join us here today, Kavita. And now we're all looking forward to hear your presentation. To the audience, I remind you to ask questions in the YouTube channel or in Discord. And with this, I hand over to you, Kavita. Welcome.
Thank you very much, and thank you for having me and the very kind introduction. I'm very excited to be here, well, except I'm not here. I'm over in Ithaca, New York, calling in remotely, but I'm very excited to share with you research that's been going on for about a decade in my group. And it spans computer graphics and computer vision, and I'll talk about all the different pieces of it and why this is a particularly good time with augmented reality, virtual reality for this research to hopefully find fruition. So let me actually take you into this video, and I hope it's not too choppy, but this is from a movie called Anon, where they introduced this concept called the mind's eye. And the idea is there's the retinal implant in the eye of the protagonist, the hero, and as he walks around the world, he sees information overlaid about every person he sees, but also every architectural detail. There's a map, there's this Corinthian capital, information about the history of this building, etc., all overlaid. Now he steps out onto the street, and there's all these overlays of advertising, of course, all on the real world, information about this car that's driving by. And back there, and you may not have noticed when it first swapped in, there were actually two women, and they are not real women. They're virtual avatars that also got swapped in when he stepped out into the street. Understanding what this car is, that's a problem called visual understanding. Being able to create a virtual avatar, that's, as you know, stuff we do in computer graphics. So as he walks farther in, let's go and take a closer look at the virtual avatars. And you can see the clothing is changing on them. He can see different styles if he wants to buy something for a friend. He starts walking down the street, and there's the name of the dog even. And you may wonder about the security of all of these apps. And it's true that that's actually a big part of what this movie questions. But that's something that is for another talk. For now, let's think about the technology that would be able to achieve this kind of augmented reality, mixed reality kind of interfaces. As he walks down the street, he looks into a window and he likes some watches. So he not only does he see what the watch is, he decides he wants to try it out. It's the Master Geographic watch. He says, I might like this or maybe not, and moves on. So I found this movie very fascinating in this interface that it's creating of this retinal implant that will overlay this rich information of the world as you go through. And I just want to talk about, what's it going to take for us as a community to make the interface, the graphics and the vision of this a reality. So there's two pieces. It's sort of, I treat them as a yin and the yang. So how to make virtual models look real. That's a problem that has existed in computer graphics forever. And virtual realism is one of the mainstays of our research agenda, which I'll talk about later. And then there's the flip side. When you see this watch, knowing that it is not only a watch, but the Master Geographic watch, that is a problem of visual understanding, and that's what computer vision deals with. So in my research agenda, as I said, I treat this as a yin and the yang. I have virtual realism on the graphics side of my research, visual understanding on the vision side of my research. And together, what binds it for me the thing that has motivated me to look at these two problems, even though they're actually quite different, they're the inverses of each other, is that I'm hoping to bring understanding of human perception to solving both of these problems. And so I'll end up actually motivating a bunch of my work by thinking about how the human beings perceive scenes when I try to motivate the work. All right, as you know, in graphics, we'll take a shape, material, light, and we'll produce an image. And where the human perception part comes in is there's an observer, and that observer has to look at that image and say, is it virtual or is it real? Now, I can't, I'm sitting in Ithaca, New York. I can't not cover the Cornell box. Introduced in 1988, it still sits in Rhodes Hall. And way back then itself, computer graphics researchers, pioneers in the field were looking at this problem as how do you tell the virtual from the real? So one of these is actually a photograph of the real Cornell box, which sits here in Rhodes Hall. And another is a rendering at that time using the technology of that time. And maybe, I don't know if you can tell, they spend a lot of effort to try to make it difficult to tell the difference. On the left is a real, on the right is a virtual. So that was from 1988, but we've come a long way from there. What makes that problem still such a pressing problem at this time in 2020? Well, it's the very complex materials that the real world is made of. So as you all know, fabrics are one example, skin is another example, food, and it's very important for us that in fact food is rendered correctly so that we can make good judgments of whether sushi is safe to eat or maybe not that fresh and maybe better not to eat. So there's been a large body of research in computer graphics to try to deal with these complex materials. I'm going to focus on one today, which has been an area of research in my group for about the past decade, and it's clothing. And I'll actually motivate it using these virtual avatars. So there's been a lot of recent interest with augmented reality and virtual reality, like that movie, on also this idea that these are called magic mirrors is a concept that's been introduced. You walk up to a mirror in some special display place or in a retail store, and not only does the mirror recognize what you're wearing, but it suggests alternatives. So it shows you the green version of that dress or completely different clothing. What would it take to make this virtual avatars be true? This also fits with that model on the left there in that image. So to understand that, we need to understand why fabrics look the way they do. So here are two pictures of purple fabric, and looking at it immediately, you will be able to tell one of them is velvet, the one on the left, and one of them is silk, the one on the right. Why can you tell the difference? So that was one of the motivating questions that brought us to this problem. What makes velvet or silk look like velvet or silk? And it turns out the answer is the structure of the material plays an important role in the appearance. So I can't help but also separately, we've been working on it also from a perception angle. I'm going to talk more about the physics-based representation today, but separately, this question of velvet versus silk has been bothering me for a long time. And here I picked two images from Hans Holbein showing depictions of people. You look at the arm of the sleeve of the clothes they're wearing. One of them is clearly velvety and one of them is silk-like. How did that artist figure out how to portray this information so that people looking at these images will immediately form an understanding of the materials they're looking at is an area of research I'm very excited about. I do want to draw your attention, if you look at the velvet, it's the rim of the velvet, it's called asperity scattering. It's very bright on the rim. That aspect is very critical to us understanding that velvet looks like velvet. Silk looks completely different. It shines in different places where the folds are. So there's another way of looking at it. That's the perceptual side. What we did in this series of projects starting in 2011 was actually look at the structure of these materials. So we went and we got CT scans. And so in the middle, you'll see different slices of a CT scan that show the structure of these materials. On the top left, you'll see the small velvet sample that we used. It's about the size of a penny. And on the right, you will see a 3D visualization of the structure as we actually we go top down, we send the slices through the 3D scans. So look at, as we start visualizing the slices of the CT scans top to bottom, first the tips of the velvet appear, because velvet consists of substrate with yarns poking up. The tips of the velvet appear, and then you slowly see the rest of the structure of the velvet, and then you get to the bottom, which is the substrate. And on the right, you see a 3D visualization of the velvet. That's velvet. Silk looks completely different. Silk consists of mutually perpendicular warps and wefts finely woven together, and that structure of them being tight in warp or weft actually makes that very shiny appearance of silk. So this is silk satin shown here on the left, and on the right is a visualization. You can see it's not protruding off the 3D into 3D space. It's tightly there. It is 3D, but it's tightly flat and woven very tightly in these X and Y directions. So once you understand that the structure of these two materials plays an important role, we thought, well, this is wonderful. What's amazing is in modern technology with micro CT scans, we're able to get this incredible rich data of the structure of these materials. And actually, it's quite cheap. It's like $200 to $300. And I should mention this was work that was done by Shuang Zhao, who was my PhD student at the time, is now a professor at UC Irvine, and Wenzel Jakob, who's also a professor now, and Steve, my colleague at Cornell. And so we said, well, these CT scans are incredibly powerful. What can we do with them? Well, they capture, if you look at what a CT scan does, here are the different slices, they capture the density information of the material. And what we did is we tried to introduce a model that can handle that density information, but you need to go beyond the density. So here's, by the way, a little part of the yarn, and you can see that's the density of the yarn in that medium. But you need optical information. You actually need also some idea of how it appears, and so you can get photographs of that. In this first paper, we actually had only one photograph that we used with the micro CT images to produce an entire fabric model using this microflake model. But in subsequent work, we've actually done more exhaustive analysis of the optical properties to have a richer appearance. So let me talk briefly about how we did it in the first paper, and then I'll talk about the more sophisticated models we built over time. So in the first work, we looked at the yarn, and in each voxel, we characterized its entire, the model we used to characterize the material had 4 parameters. And this was the microflake model that we introduced, where the 4 parameters were based, the idea was like the microfacets, there were microflakes, and they had a density shown on the left, an orientation shown on the left in the middle, some spread of the flakes shown in the middle on the right, and an albedo shown on the right. And it turns out that once you have these 4 parameters, you can get these values by combining an analysis of the structure and the images. So the left 2 values can be found by doing, they're related to the fiber, the arrangement of the fibers in the CT scans, and the right 2 can be obtained from photographs. So if you do some CT image processing, you can get an estimates of these density and orientation. And if you take appearance matching between photographs and your rendered models, you can actually get the other 2 values. Once you do that, and I know I'm going through this in a higher level, please do look at these papers. There's a bunch of papers on this that actually give details on it. But once you combine these 2, you now have a complete model that captures the structure of velvet and silk. And you can see on the top, on the rim of velvet, there's that asperity scattering, which is exactly what was shown by those artists in their paintings. And silk has these highlights, also in the same location, but you can tell that they're different. And that's how you can tell these materials apart. And so I'll show you now just an animation of these. Hopefully it'll come through without being too choppy. And you can get a sense of feel of the material just by moving these pivoting them around. How light interacts with it gives you a good sense of the materials. So after that first foray in that work, our next step was actually to generalize this work to deal with arbitrary weave patterns. And you can see here 2 different weave patterns. I particularly want to point out to you the one on the top left, that pillow. It looks like there are 2 different colors of thread there, right? The dark and the light. Actually, the yarns there have only one color. It's the structure of the weave pattern, whether it's more aligned with the warps or more aligned with the wefts, that actually conveys this very complex appearance like it's 2 different colors. I've always found this particularly fascinating because that just really tells you that you need to capture the structure accurately rather than trying to approximate it, because you'll never be able to understand that one yarn can produce 2 such different appearances. It's the structure that matters. In follow-up work, so that was the body of work that used the CT scans. Our next step was to try to come up with tighter representations. The CT scans are a pretty heavy representation. And so we went and did a further analysis of these yarns, and yarns are made of plies that are twisted together. plies are made of fibers that are twisted together. And it turns out these fiber level details are actually very important to capture for realistic appearance. So in follow-up work, we introduced very detailed models of how fabrics work by modeling the yarns, plies, and fibers explicitly. So I'll give you a hint of how that process works. So once you have these fibers, they have a cross section, they migrate and they twist, and there's also flyaway fibers, which you've seen with fuzzy materials. So we take that as a model to combine them together to form the plies. The plies then have a cross section that can be twisted together to form the yarns, and you get the yarns on the right. So that's sort of the forward model, the procedural model that you can introduce for the yarns. What's hard, though, in this, there's only 22 parameters, which makes it very powerful instead of the very heavy-duty 3D volume data. However, the challenge is, of course, finding these 22 parameters is non-trivial. So what we introduced is actually a method to fit these procedural yarn models so that you can get powerful models that can help you with editing for fabrics. So what we did is we actually took CT scans of these individual yarns, shown here on the right, actually mounted on some thermocol. So we took those CT scans of them, did some fitting to get the yarns out of them, go back and do ply level fitting. So figure out what the plies are, untwist the plies out. So you can see those two untwisted plies at the bottom, coming from understanding the cross section and the twist together. And then going further back to understand the fibers that contribute to the plies by looking at the cross-sectional distribution of that, looking at the migration of the fibers, and coming up with models for the flyaway fibers. So this may seem complicated, and it is, but it is a very powerful then representation that lets you do very interesting things that were hard to do before. So one example of what you can now do is once you have these models, you can actually modify yarns and completely change the appearance of the material. So for example, here are two silks. On the left is, by the way, the photograph of the silk. On the right is what came after we ran our whole process and came up with the model. And if you have a fabric that's made of a woven combination of these two yarns, then you can edit the yarns, change their twist, for example, here, and then produce a new fabric. And you can see the new fabric is a lot shinier. Its appearance is very different. So the reason we introduced these techniques is we felt it was important to give these kinds of tools to textile designers so that they can do virtual prototyping, see the effect of changing the appearance of yarns, etc., and produce what it would look like without having to go and actually produce the yarn in person and then look at it. And at this time of pandemic, actually, this kind of virtual prototyping is particularly compelling. And I see this as an important, will continue to remain as an important goal, I think, in our industries. And so to step back, that was our goal. There is a real production pipeline that you use in an industrial loom. You have a loom, you have these physical yarns, you have a weave pattern that gets fed to the loom, and out pops real fabric. And our goal was to create a virtual pipeline that essentially matched that. We had essentially a virtual scans of a database of scanned physical materials, of scanned yarns. We would combine it with the weave pattern and produce an output that hopefully was indistinguishable from the real fabric. So here is a left and right comparison of the real fabric and the virtual fabric. And I hope that you will accept or you will believe that, in fact, we've done a good job. They're not an exact match. There's some issues with the color matching. But actually, in terms of conveying the texture, the irregularities, sort of the feel of the fabric, the virtual and the real are hopefully very close to each other so that you can make good decisions when you're doing digital prototyping or textile design. And just so to give you the information, the one on the left is the real, and the one on the right is virtual. So as I said, this is a body of work that's been in my group for a while. There's lots of other great researchers who are doing wonderful work in this space, and this list doesn't even do justice to them. And as next steps, there's a lot of interesting work that other groups have been actually doing on understanding the mechanics of fabrics, which I also think is very critical as we go forward. So getting back to sort of this virtual avatar goal, if you remember, as I said, one of the goals is making these virtual fabrics look real, which I hope you will believe that we have taken some of the steps to getting there. But as I said, there's still a way to go. There's another piece of it that's actually interesting. In this virtual mirror, you walk up to a mirror and it should recognize what you're wearing right now, recognize its fabric, but also recognize the material parameters so that you can edit on the fly and suggest alternatives to a person. So how do you enable material editing with these very, very complex materials is an interesting question. And so I'll just briefly give you an idea of some of the work we're doing in this space. So you could imagine that we could try to do everything with the full physics, but the problem is that's actually slow and it's not that easy to do. Separately, of course, all of you know there's been this revolution going on in deep learning. And so the question is, the learning-based, it's good to be able to leverage learning-based methods if they are available. The one hesitation I have with pure learning-based approaches is that they actually ignore the physics. And that's a shame because the physics captures very important aspects of the material that you don't want to lose and try to learn with a very, very brute force data-driven approach. So in my research and with collaborators, I've been working with Shuang and Yanis Galakis on this. We've been trying to look at this question of can you combine the physics with learning-based approaches? So I'll briefly give you a hint of sort of some work that we've been doing in this space. It's called inverse transport networks, and we just recently presented it virtually at ICCP. And so the idea that we're trying to solve is somebody presents an image, and we want to infer the real physical material parameters that should have some physical meaning to them. So in this case, we were looking at scattering, and so we were looking at the scattering parameters, the Hennier-Greenstein function, etc., as the values we want to get out of, hopefully, a learned network. So how would you learn such a network so that it produced physical parameters? So we introduced the inverse transport network that essentially combines this learned part to a representation of the materials in the middle there, material pi, with a differentiable renderer at the other end. So the renderer R is a differentiable renderer. It takes geometry and lighting and produces images. And what you can do is in your training of that neural network, you can set up the problem to be so that you match the output image to the input image. For the output image to match the input image, the hope is that that neural network will actually produce parameters that are physically accurate so that when you feed it to the renderer, it produces an exact match. Now, that's only one piece of the loss function we use. There's a little more to regularize a function, so you should go and look at the paper. But the high-level idea is essentially we're trying to learn in this neural network something that's inverting the scattering process, hopefully on the fly. So we have some, as I said, our goal really is to combine physics and learning, which I think is a very powerful future direction in this space. When you're doing your testing, by the way, you just have your input image, your network very, very fast produces some material estimates. To give you an idea, there's much more detailed results in the paper. To give you an idea of how well this works, here's the ground truth. It's actually a photograph of a pretty complex sort of slab of, complex in its shape, a slab of a translucent material. And on the right are the matches we found. It's not a perfect match, but it's a good estimate to get started for something that's on the fly, not in a laboratory setting, and fast. And it does not require any understanding of the geometry and lighting. Hopefully, these will get more sophisticated as you go forward. So that gives you a flavor of some of the work I've done in this space. There's a lot more work that I won't have a time to talk about today on material modeling and editing. But I'll give you, I'll sort of wrap up this part of my talk, which is the graphic side of the talk, so that I can now spend some time on the vision side of the talk. So as I said, my goal is this idea of achieving virtual realism using knowledge of human perception. And going forward, I really do believe that we need to close within our community, particularly where we have a very great appreciation of the physics of how light interacts with materials, how things move. While I greatly value learning-based approaches, figuring out how to combine these is what I think will result in the most powerful kind of solutions, particularly in these augmented reality, virtual reality, mixed reality settings. Okay, so that's one half of my research. Let me talk about the other side now. When you have a photograph, what can you understand of what you're seeing in that photograph is the problem of visual understanding. And as I said, that's a problem that computer vision looks at. So, as the protagonist was walking down the street, he came up to this window and he looked at all the items in it. And in his eye, in his mind's eye, so to speak, up popped the annotation that not only is this a watch, this is the Master Geographic watch. So that, as a human being, most of you, when you look at this picture, can tell it's a watch. But most of us will not know that it's a specific brand or a specific kind of a watch. That typically requires expert level knowledge. You really need to know your watches to be able to identify exactly which watch this is. This problem actually of recognizing at the expert level doing recognition is called fine-grained recognition, and it arises in multiple domains. So one domain is on the right here. You take a picture of somebody and you want to understand, gee, what is that handbag that woman is carrying? Or in the middle, in interior design, you want to redo your home, you go to a site like House or other sites like that. You see something you really like. Often, many consumers and people who are shopping the sites will write out questions like, what is that countertop? I'd really like to know what it is. So how do you solve that problem of recognizing these arbitrary objects that you see in different images? That was a problem that we set out to address in this research that I did with Sean Bell, starting in 2015. And I'll sort of describe the arc of our research. It became our company Grokstyle that got acquired last year, as Ulf mentioned. So the problem, as I said, is called not only object recognition, but it's fine-grained object recognition. So we actually set out to solve the problem in the context of home decor. So say you walk to your neighbor's backyard, you see this thing, and you don't know what this thing is. So you take a picture of it and say, what is this? What we set out to solve is the problem of returning to you this information. It's the great bowl of fire, entirely based on the visual pixels we were seeing with no extra information. We wanted to return to you the answer. It's a sculptural fire bowl, it's a fire pit, and this is where you can buy it. There's a next step. Say you figure out it's a fire pit. You might ask one more question. Gee, I wonder, that's one way of using it. What are the other ways of using it? Now, with the fire pit, maybe there are not that many ways of design considerations. But even with the fire pit, actually, there's two different ways of using it. You can put it bang down in the center, as done in the image on the top, or you can use it sort of as lanterns in different locations. So these ideas of design suggestions that can come by looking at how different people use it can give you design inspiration, which is valuable, say, when you're redesigning your home. So it turns out that answering both these questions requires the same technology. And so that's why we rolled it into one problem. So now I'll give you an intuition of how we solve that problem. So first, let me tell you what the challenge is. You have all of these images of these various products, and it turns out you can actually think of them as two types of images. These sort of clean images, like we're shown on the left, they're called the clean product images. They come from the manufacturer's catalog. They're called iconic images. And then there are the images on the right, which users take on and they post it on Instagram, on Facebook, on whichever social media site that's their favorite. They are messy, they're in the wild, they're taken in different lighting conditions, different camera resolutions, etc. Your goal is try to figure out, when you look at one of those pictures on the right, exactly what it corresponds to to the product on the left. And so our solution, which we introduced in 2015, was to train this, using deep learning, to train a Siamese network. So there's two networks that are matched, hence the term Siamese, to learn how to match these two. So I'll give you an intuition of how the problem works, and then I'll talk about our solution. So when you're saying you're using learning, what are you learning? You're learning a projection. So there's this high dimensional embedding, and you're learning a projection function, so that each image has sort of a fingerprint associated with it, and it projects to one location in the embedding. Now, what you want to learn is the same product. So that image of that chandelier on the left matches all those images on the right. And so you want all of those images to project to the same location in this high dimensional embedding place, ideally. And some different product will map to a different location so that you can tell them apart. If they're not in the same location, they're probably not the same thing. Here's another location. So that's the high level goal of what you're trying to learn, this projection in this joint embedding space. Say you were able to learn it, and I'll talk briefly about how you do that, but say you're able to learn it, how can you use it? So one is, you can search now using the embedding. So if somebody comes with a picture saying, what is this picture? You can project it into the embedding and go and retrieve the information associated with that product in the catalog. In this case, you can say it's a Hemel ring, it's a hanging light. sold by this particular person. So that's one path. The flip side, you can go in the other direction. Somebody comes and says, gee, I'm planning to buy this thing. Where all have people used it? You can go back, look at all the images and show them the full images, not just these crops, so that they can understand what kind of decor it goes with. Maybe it's a little more Gothic, maybe a little more Baroque in its style. And so it gives you design inspiration. Okay, so that's the problem setup. Let me talk about how you would actually learn this embedding. So we used, and many of you know this, but we used a contrastive loss, and it's based on the work by Haskell. So the idea is you take this picture in context. As I said, there's a whole image, but there's the product, which is cropped there. And you put it through this CNN, the convolutional neural net at that time, with these parameters, and it projects to a particular location in the embedding. So far, so good. How do you actually learn that products are a certain thing? Well, so you set up two types of losses. One is when you have a positive example. So here's an iconic product, which is the same product as that other product. Now you can see pixel-wise, those two images look different of the product, but they are actually the same product. As a human being, you can tell they look pretty similar. So that also projects to a different location in the embedding. And you set up a loss so that this loss function pulls these 2 points together. In an ideal universe, they would actually sit exactly on top of each other because they represent the same product. So the loss function encourages that by pulling the two of them together for a positive pair. For a negative pair, on the other hand, you have that same product, but you have an iconic image that does not match that product. You want to see where that lands, and it seems to be landing in the same point of the embedding. You want to push it apart and push it beyond, in fact, the margin, a certain margin M, using a loss function like this one shown here. So that'll push these two apart, the negative examples, and pull the positive examples together. So when we first wrote this paper, that's what we set up. And then we did 2 weeks of training with our university level compute resources, and we trained a whole system. So just to give you an idea, all the embedding stuff that I told you and the contrastive loss is one loss. We also added another loss, which is based on recognizing the categories of the particular product that you're seeing. I'll refer you to the paper for details. But the idea is that you have the Siamese network, which are the two CNNs that are mirror copies of each other. You have two losses, one, this pushing loss called the contrastive loss, and the other is this category loss. And if you train that system end to end, you learn an embedding that recognizes products. So I'll first give you a hint of how those results look. As I said, this embedding is this higher dimensional surface, if you will. You can project it down to 2D, and you can visualize it using what is called a T-SNE visualization. And here's our T-SNE visualization. You can see there was a lot of structure in certain parts of it. And then when you zoom in on any part, you can see that all the plant-like things are together, all the pointy-like objects are together, all the down-facing lamps are together. So you can see that this 2D projection actually seems to have captured the structure of similar things getting grouped into similar parts of the embedding space. So that's good. Let me now describe sort of some of the results. I'll show you actually qualitatively some of the results. So say you walk into a room like this and you say, hey, this is a beautiful room. I would love to get that chair over there. And so you take that chair and you send as a query this chair to the program. I like this chair for a few reasons. It's transparent essentially. So what it's showing primarily is actually the pixels behind the chair. There's not that much chair there. So it's a very hard problem. And so it's one of my favorite examples. I've actually bought chairs like this because of this research. And given this query, our system gives the following results. You can see it has identified this as this popular chair called a ghost chair, exactly because you can't see much of the chair. And in fact, the third entry is the exact match because it matches, all three of them are good matches because they're ghost chairs. But that third entry with the handles is the exact match with the arm sides. And that exactly shows what it is. Here's another example. You may walk into a house and say, I really like this thing. It's very hard to describe what that chandelier is. And it's very hard to describe it to some other person in words, what you like about it or how it looks. It turns out queries like that are very straightforward with visual matching. It turns out this particular chandelier is called the tiara chandelier. And we correctly find it as the first answer that we respond to. So we built this visual search research, and then we went out and floated a company, GrokStyle. Sean and I co-founded it, where we then actually partnered with IKEA to show off how visual search and recommendation-based systems could work in augmented reality. And this augmented reality theme is one of the common themes of a lot of the research that I do. Now, it turns out for furniture and home decor, augmented reality is particularly important because people don't have a good sense of space, and it's a place where understanding how things fit in context gives them a critical sense of, gee, am I overcrowding this room, or will it look good? So we had a visual search, we added recommendations, and we did recognition of the fly, and so you can see what our results look like. Here in this armchair, we recognize automatically the cushion, the Strandman chair, and we can also, once we do that, combine it with reconstruction to show different designs and different colors. Now, this color matching does not use our research, so that was from IKEA's app, so just so you're aware. You can also complete the look. You can add an ottoman, you can add a side chair. And so the point is, this kind of technology lets you explore design spaces in a very natural, intuitive way, in a way that didn't exist before. So everybody can feel a little more comfortable before they spend thousands of dollars buying new furniture. So GrokStyle got acquired by Facebook last year, and actually very timely and unexpectedly. Last week, Facebook, actually, Mark Zuckerberg announced GrokNet, which is based on GrokStyle's research, and Sean is leading this project in Facebook on Facebook's new shopping AI. Their goal, as was GrokStyle's goal, was to make every image shoppable. And I showed it here because it actually, you can see, it's very powerful. So it on the top left is some idea of the architecture. There are 83 losses instead of the small number of losses I showed you earlier. They build off 7 huge data sets that are amazing. And then they can recognize things like this rose pink tea kettle. Of interest, though, is that these loss functions are similar, inspired by the previous one, but actually go beyond that. So this is a double margin loss function. They have a KDD paper on this that I encourage you to read that actually achieves very high performance and will hopefully make every image shoppable. So that's that story arc. And this idea of making every image shoppable was one of the goals of GrokStyle. But all along in my research, I've been actually stepping back and thinking about a deeper problem, which is I would like to make all images fully understandable. So what does that mean? So let's just step back. We are documenting our lives at an unprecedented scale. So if you think of the amount of data we upload of our personal lives to the cloud on a daily basis, it is just staggering how much information, visual information there is about the entire world, not only about one location or one set of people. So on the left is data from 2020, 95 million photographs are uploaded daily on Instagram. So this question that I've been asking with some of my colleagues, and started with Noah Snavely, and I'm working with Bharat Hariharan on this, and Utkarsh and Kevin. Kevin was a student now at Facebook. Utkarsh is a current student of our group. Is given all of this amazing data, what can I understand about the world? So you can think of a future anthropologist going through this data. What can they discover just by looking at all of this visual data? Turns out they can discover a lot. They can discover what the world was made of. What are the kinds of objects and things that we had in our daily lives? How do we live? What do we wear? What do we eat? Who are our friends? Who do we hang out with? How does our behavior change over time? So there's an astounding amount of information, and actually we're working with a cultural anthropologist to study with some questions of how people in different parts of the world behave similarly and differently on different topics and different occasions. That's one of the research questions that motivates me. So I'll talk about one project in this space, is just understanding how different people across the world dress. So what we did here is we collected Instagram data from 36 cities. So we collected about 8 million pictures. And for each of these pictures, we used an off-the-shelf face detector primarily, and you can make it privacy preserving. And I understand that's an important concern. So that you can find a face and just ignoring the face, look at what's the body wearing underneath that face. So what are the clothes that the person is wearing? If a picture had too many people, we actually in our first cut, we just focused on single selfies and ignored the face and looked at what people were wearing around the world. To then analyze what people are wearing, we collected a very small data set, 27,000 annotations on mTurk with clothing attributes. So 12 attributes each, and I'll give you a feel for the attributes. Are people wearing scarves? Are the neckline that they're wearing, is it a V-neck? Are they wearing a particular color, green versus orange versus black? Are they wearing dresses? So the whole list of attributes is down there. We looked at patterns, etc. So given this training data, we then trained a CNN using supervision with our annotations to then come up with learning this embedding. And here's this 2D projection called the T-SNE visualization of this embedding. What makes it interesting is, so let's look at this visualization. Let's zoom in on parts of it. So even though you can't see all the details, you can, I think, see that on the top right circle, there's sort of a lot of green stuff, for example. On the bottom left, there's a lot of red. In that middle oval, there's a lot of white. And so it turns out there is, in fact, this embedding is capturing a lot of interesting visual appearance of the clothing that people are wearing around the world. So that was our first, you can learn this embedding. Then you can go one step further. So you can use an unsupervised Gaussian mixture model to find different style clusters. So you can set some set of clusters, we chose 400. You can do more research on that space, to find finer grained style clusters within this learned embedding. So for example, you can find a cluster of plaid clothes, but you can also find combinations, like people who wear layered clothes along with jackets, with a certain dark jacket, light shirt, or dark jacket, certain kind of t-shirt look. You can find striped clothing, etc. So this is the first level of analysis. What can we do with this information? As I said, it actually is a fascinating sort of window in how the world exists around the globe. So we started then looking at individual style clusters. So on the left are 4 of the top clusters that have a lot of sort of purity to them. And in each cluster on the left, we showed on the right a mapping of the city on the x-axis and the month in which those pictures were taken. Because we know where the pictures were taken with geotags and the month they were taken in, we can just light up this graph on the right based on those images on the left. So for the top cluster, what's interesting is you can see there's one city, no matter which month, that really lights up. It turns out that's Lagos. And that first style cluster has this headgear that's very distinctive to Lagos. And if you were there, you would know it. If you've never visited, now you have a little more cultural understanding of how people dress there. The second 2 rows are women wearing a hijab. It turns out that there are several countries in which people wear hijab, but in Cairo and Jakarta, it's extremely prevalent. So again, if you were to visit there and you've never been before, this gives you an understanding of the culture and the local customs of the place before you even set foot there. And finally, the last one is interesting in a different way. It doesn't light up in a particular city, but it does light up at particular times of the year. And when you look at the cluster, it's pretty obvious. It's warm weather, it's cold weather clothing that you're wearing to stay warm. So is jackets and hats. And on the right, you can see January, February, and November and December are where it lights up at different cities. And in fact, in a further analysis, which is in the paper, you can see northern cities behave exactly conversely to southern cities in the southern hemisphere, as you would expect. So those are sort of unique style clusters. Then there are the style clusters that are ubiquitous, that all the world shares common fashion. And what are those clusters? Here are examples. So everybody in the world wears blue shirts for, formal dressing, blue button-down shirts. They wear black t-shirts with, that's the second row, black t-shirts with some sort of graphic on them. Plaids are very popular everywhere in the world. And bottom is all black t-shirts, again, very popular across all cities. Some cities maybe more so than others. So that's also very fascinating. You find out what's common across the planet and what makes us different across the planet. We further went and did some more analysis. So one thing that you can do is study unique events. So for example, we were just analyzing different kinds of dresses, and we noticed there was a big spike in t-shirts, yellow t-shirts with V-neck and a graphics on them in this particular month in 2014. Now, if I were there with you, I would ask the audience, what do you think this event is? And typically people do get it, particularly if it's in Europe. But since I'm not there, I'm just going to tell you, as you probably guessed, it's the World Cup. So at the time of the World Cup, everybody was wearing these yellow shirts with this graphic, or they were sharing pictures of their favorite heroes wearing those clothes. And so you can also see when you map it on different parts of the world, which parts of the world it really captured their imagination, and which parts of the world maybe, they didn't care as much about the World Cup. I know that might be sacrilege for some people. So this was fascinating, and for us, we felt like we were discovering things about our fellow human beings that then motivated us to our next project. So this project was called Street Style. In our next project called GeoStyle, which we just published in ICCV, we said let's do automatic discovery of these trends. So if some big spike happens, can we discover it automatically? So let me give you a flavor of how that paper works. So we do all of this attribute recognition, the style discovery that I talked about earlier in Street Style. And then we look at these graphs. So on the x-axis is time, and on the y-axis is popularity. And this graph happens to show for Moscow, people wearing hats. And so you see two things automatically. First, there's a very cyclical trend, which makes a lot of sense. In winter, people wear more, furry hats. In summer, they don't. So you see that. But you also see these big spikes. And these big spikes correspond to people taking pictures of themselves on special events like New Year's or Christmas, even though it's very bitterly cold. They've got their hats on and they're taking pictures. So that was, and we can automatically now discover. So what we did is we introduced a technique to automatically discover these kinds of cyclical patterns. And I won't get into the details, but this gives you an idea of the kind of function you can fit to it to get an idea of cyclical patterns with a little linear trend to them. And then additionally, we can find big spikes too, which are the outliers. For example, here is a plot of people wearing green. And you can see big spikes around St. Patrick's Day, which is March 17th. And it just pops right out of the data. And, something important happened in Chicago where everybody showed up wearing green on that day. And I'm sure there are equivalent across the world. So once you have that approach, actually, I'll give you a few more trends that we found automatically. So one was we were looking at Seattle data, sleeveless clothing, and there's this regular seasonal behavior. In summer, people wear seasonal clothing, sleeveless clothes. That makes total sense. And then there's this odd spike during winter, shown here in green, where actually people wear sleeveless clothes when it's actually quite cold. And it turns out it's something called Freak Night in Seattle, which I didn't know about. And I now discovered a cultural phenomenon where everybody dresses very outrageously and posts pictures of themselves. There's another one, which is we analyzed Bangkok and people wearing yellow. And there was this big spike in yellow in December. And we were trying to understand what that was. Turns out this cluster shows it. It's Father's Day because it happens to be the king's birthday in that time, which is not when the rest of the world celebrates Father's Day, but it's when they celebrate Father's Day in Bangkok and they wear these dad t-shirts and go biking on that day, and it pops right out of the data. So for us, this ability to automatically find these trends by doing an analysis of the data was just very eye-opening. So there's lots of different cultural events that show up on the world. I encourage you to go to our website, geostyle.cs.cornell.edu, and check out the different, we can browse some of the data too. You can see Paris, there's Vogue fashion in 2015 June. There's a particular religious events in India in 2013 in October, the Melbourne Cup in Sydney in 2014 in November. And all of these dates correspond to the time when we had clean data from Instagram. So it's from 2013 to 2016. That's why there aren't more recent dates. This is a data set we've actually made publicly available. Here are the top 5, and you can see, as I told you, there's a World Cup is the bottom row, Father's Day is on the top, and there are other examples that you can look at. I'll give you one more example that I found really fascinating, and this might hit closer to home for several of you. While we were doing this, we actually ran all this on Instagram, but then ran the same algorithm, but on Flickr data, and out popped a political rally that we actually weren't aware of, and this just came out of the data. So it discovered a political protest called the Catalan Way in 2013 in Spain, where everybody formed a human chain wearing yellow. We, living in the US, didn't actually know about this protest, but the data just told us about it by automatically being discovered. So I find this, the cultural implications, understanding the world and what brings us together and what makes us different, fascinating. As I said, we're working with a cultural anthropologist. And in the future, I believe that, beyond just looking at what we wear, it's interesting to think about how are our behaviors changing over time. For example, We don't have the Instagram data now, but if you did, I bet you have lots of pictures of people with face masks out for an anthropologist in the future to understand how we adapted to our times. We are actually now taking this kind of technology and applying it for satellite imagery to understand how the planet has been changing and using it for crop analysis, etc., to find if there are anomalous behaviors that we should be using to do discovery that's useful to agriculturists. So that's what I have to share with all of you today. My research over the past 2 decades has been on actually leading to this point of, making the kinds of technologies that make augmented reality, mixed reality, VR, a true reality. And there's there's an interesting time right now. Again, there's a lot of discovery going on around the space where we might be taking the leap to making more of it real and more available to general consumers that I find very exciting, so that people can discover things that they could not discover before. And I see this combination of bringing physics and learning and discovery together as a very exciting space for future research. So thank you for listening. I should say I have incredible collaborators, students, and several of them are now my ex-students who have really enjoyed working with. And so this is some fraction of them, not all of them, but these are the people whose work I spoke about today. So I'm going to pause here now and wait for Ulf to ask me questions.
Okay. Now you can hear me, right, Kavita?
I can hear you now. Yes.
Okay, wonderful. So thank you so much, Kavita. Let's give Kavita a big round of virtual applause. Yeah, I see here coming up on the YouTube channel, lots of these hand clap, and also we use here the hand wash symbol for showing appreciation.
Thank you.
So everyone, it's time to post your questions. You can do that on Discord or directly on this YouTube channel. And we already have one question, and that is, these results are very interesting. Have you tried tackling polished metal surfaces? And to understand the question, I think it was quite early in your presentation, might have to do with the CT scans and yarn modelings.
Good. So actually, in this context of the CT scan, some materials are better than others to get the full structure. In the context of metals, right, there's been a lot of great work on speckles and sparkles that actually Wenzel and Steve and a bunch of other people, Ravi Ramurthy, have done on, which has been a parallel line, which has, I think, really pushed the state of the art on representing them. And a bunch of the people actually on this slide are also involved with that, Chuang, for example. So we haven't done that in the context of CT, but there exist solutions for that. And the next wave of that kind of research is also looking at wave optics, which makes a lot of sense because you need to get into those level of details to start to really capture them
well. Okay. Then we have what happened to the sound?
I can hear you. Can you hear me?
Yeah, now I can hear you.
Okay, good.
Okay, so let's take the second question. So when exploiting learning so much, what about bias, colored, white, rich, poor, internet, disconnected,
very good,
rural,
really
urban?
Good questions. Yes, absolutely. So that's exactly a very, very important question, actually, and it's actually one of the things I hope to explore with this cultural anthropologist. An example is we're looking at people. So bias, there's various ways to think about the phrase bias. Let me take one sort of an innocuous example. Younger people post a lot more pictures of themselves. Teenagers post way too many pictures of themselves, and older people don't actually typically post that much of themselves. So that actually shows up in whether, when you're trying to understand the traditional dresses in different parts of the world, it's not so clear you get the same representation of how much people dress in the traditional garbs, because the traditional people typically don't post pictures of themselves as much as the more westernized clothes, right, that people wear. So that's one example where bias does come in, and we actually try to look at trying to understand that aspect of it. So when you work with an anthropologist, as we're doing, you actually cross-correlate that with other data that corresponds to their understanding of that particular culture, and you have to bring those two together to make progress to actually really getting solid measurements that you can actually claim are measurements. Right now, these are not measurements; these are more they give you a feel or a flavor of the kinds of things that happen in particular parts of the world. It's not something that you could actually take measurements on, but you can correlate with other kinds of data to address that. When we're looking at satellite imagery and stuff, actually the sampling is very different. So the sampling stops being this irregular sampling that is prone to bias. Now there's much more regular grid-like sampling, and then we are able to actually come up with better measurements that are more accurate to the space. So it is a question that, if you shouldn't go and look at those graphs and say the y-axis said this, therefore that's the quantity, but it gives you a flavor. There are other forms of bias. There's lots of issues around actually whether or not the recognition works across the board. So the assumption was we were assuming that the recognition can find the people. If it doesn't work for certain colors of people, and actually my skin color is in that category, then what are you supposed to do? You're not measuring those people. It turns out because of geolocation, you actually do measure. In India, there's lots of pictures of Indians. You do recognize a lot of the images of the people that are there, but it is something, again, there's a lot of interesting work around creating balanced data sets that can work in recognition across the board. So it's a very interesting and open problem, and more work needs to get done there. But you can correlate with other forms of data that hopefully then gives you more accurate measures, is the short sort of version of it.
All right, thank you. So the next question is, what will future trends be for material appearance modeling?
For the actual research area, is that the question?
Yeah, it just says that. What will future trends be for material appearance modeling?
Yeah, so I do believe that closing this loop, the full loop, closing the most beautiful models we have, and we should keep them because they capture appearance at a level that has not been done before. So I really like the physics-based models. I really like that they capture a level of detail that a human being, when they go close to something, will notice, but the coarse mechanisms that are out there don't. So I like that. As I said, one of the things that I think, though, is important, it's hard to deny sort of the lure of these learning-based techniques that are so powerful. So I hope that the way to do it is to combine the two, is that you have these physics-based representations. You learn perhaps interpretable models. That's what I would hope. And they could be two types of interpretations: perceptual interpretations, or perceptually valid models, or physically valid models. Both are fine depending on what your use case is. And if you learn both of these kinds of models and combine it with more learned techniques, I think that's when you get the best of both worlds. And so that, to me, I feel is the path forward, at least in the kinds of research I'm excited about exploring. I think it can yield a lot of great dividends.
Okay, thanks. So maybe that answers the next question, but I will post it, tell it anyway. So could you leverage visual appearance using the material structure ideas from the first part of the talk?
Yes, you mean and combine it with learning? Absolutely. I think that's the way to go. I think that's the question, right? Just confirming that I understood it correctly.
Yeah. There's a final question. Which problems of material appearance modeling should we handle with deep learning?
Yeah, it's related. I'm hoping. So first, you got to get your differentiable renderers to deal, and it's important to have them in the inner loop of the learning. Once they're fully powerful and can deal with all the complexity of all of the rendering algorithms, and there's performance issues, there's various aspects of it, the full GI, etc., and all the complex materials. If you can have that, so that's one big challenge. If you have that, then end to end, you can start building systems where you have these interpretable models that fit nicely. Now, the question is, do you need the full glory of this, or can you get away with approximations? I think that's all a good question. We don't know the answer to that. That's the research that we'll have to do to see if we can do better, or whether we need to do the full end-to-end thing.
Mm-hmm. Okay. So one more question. For object recognition, what types of objects or perhaps materials or something else are hardest to make work?
Actually, and somebody else had asked this question earlier about bias. I started talking about skin color. There's another sort of bias. There's some very nice work on this. All the pictures I showed you, but these beautiful houses. I don't have a house that pretty. I have kids in my house, and clutter is very difficult. So when an environment is very cluttered and there's lots of small objects, finding them is hard. That remains one of those challenges. And what what the community has been trying to do, and when I say we, I mean the community broadly, is trying to broaden those kinds of data sets to make them make it so that we can do detection of all the cluttered little objects, all the messy things that are not beautiful catalog level imagery. So that full understanding in every environment. And this is actually when we did our material recognition work, apart from taking pictures from house and domains like that, there were a bunch of domains that are sort of high-end images. We also looked at, Flickr open source images, which really show people in villages and in small huts with kitchens, outdoor kitchens, etc. And we really getting that mix of data in was very critical. So I think those are the kinds of areas, getting those real world settings across the world more integrated in is going to be critical to actually achieve this sort of fully realizable, making all images fully understandable goal.
Okay, thanks. They're popping in more questions. So what is the role of human vision in this virtual realism / visual understanding? How much consideration of human vision can contribute to the way we render in CG, and how much inspiration CV can get from it?
That's great. And that is sort of my lifelong sort of research goal, right? I don't have an answer to it. I think it is important. So in the early days, so I'll talk about the deep learning side. In the early days, there was a hope that they'll be aligned with vision, and it actually vanished, right? It just, the data-driven approaches are very powerful. Doesn't need to have a connection with how vision works. But there is some body of work that's trying to connect up pieces of how these algorithms learn with human vision. And I'm very interested in actually exploring that. So I showed you those two examples of those paintings of, and so we have a project that we're working with folks in Delft on looking at old masters paintings. They were amazing in conveying material and shape. What did they mean? It's 400 years ago. They were drawing beautiful imagery where they understood the essence of materials and could convey that with a little white paint here and a little blue paint there. So if we can understand what they understood of materials and actually use that in the representations we learn, I think we can have more generalizable learning algorithms that will actually be more robust. They might not be the best state of the art with every 0.02% gain, but they might be more robust the way humans are robust to understanding in very broad sets of settings. So that's on that side. That's how I see perception playing a role there. On the graphics side, I feel perception has always driven graphics research. In some implicit sense, you produce an image that matches what a person will perceive rather than necessarily the radiometrically most accurate version of it. So the history of perception and how that influences image quality metrics is, I think, fundamental to graphics, and that will persist. And hopefully we can come up with models that are tailored to our appreciations of material. So for example, if we really get to these AR VR settings, then based on where our fovea is, we can change the quality that we're rendering, we can change the simulation quality, etc. There's a lot of beautiful research that people are doing in that space. I think that'll actually become more important as these AR VR realities become a reality.
All right, thank you so much. So yeah, we have no more questions for them at the moment. So we have come to the end of this keynote presentation.
Thank you very much.
Oh yeah, actually there is one more question, and I think we have a couple of minutes, so no rush. Why did you specifically choose silk / velvet fabric for your research and not other materials like fur, leather, wool, cotton? Just curious to know the reasoning behind that choice.
Actually, we did all of the above. I talk about silk and velvet because you can see them side to side. It serves as an illustrative example. But in the work that we're doing in analyzing the old masters, we're going to do all the materials. People are not very good at telling cotton versus, so we've actually, the perception of silk versus velvet is very clear. If I were to ask you cotton versus in some conditions wool, it's not clear you'd be able to tell just by visually. You might have to touch it. And that's a whole separate area of haptics. So I use it as an illustrative example, but actually we run it for all of the materials. The methodologies for the CT scans, et cetera, apply across the board. And in our perceptual studies, we try to analyze across all the ranges of materials. I just use this as an example because it's very obvious to a visual. No matter how much the degradation over YouTube is, you can still see velvet versus silk typically.
All right, thank you. And I've been also asked to extend thanks from the whole Eurographics community to you, Kavita, for coming here. Wonderful.
Thank you very much. I'm so sorry I could not be there in person, but I'm very grateful to all of you for tuning in. And please feel free to send me questions. I'm happy to answer them. I won't be there in person, but you can look up my email and send me email questions if you'd like.
All right. And thank you everyone for attending and coming here today. So let's again give a big round of virtual applause. And yeah, you already have got a big round in the YouTube channel. So I hope all of you will enjoy the rest of this afternoon and the rest of the week. So with that, I say bye-bye everyone, and thanks again.
Bye, take care.